Hi everyone. So today I'll be talking about collaborative bandits. Um, at a high level, the theme of this talk is how do you handle missing features or missing contextual information in bandits. So in real world, data is always missing. So typically in theory, we don't consider these problems, and it's very important to design algorithms that work well even with missing data. So most of the problems, so this talk is meant to be a very high level talk. So I'll try to go into theoretical details as much as possible, but feel free to stop me if you want to know more about something. This is meant to give you a overview of what are some of the open problems in this field and what could be interesting from a theoretical perspective. Okay, so this work is mostly done with my wonderful collaborators at DeepMind. So you might have already met or seen Aparna's talk yesterday, and some of the work I'm going to talk about is also based on our collaboration together. Yeah, so here is the outline of my talk. So I will first try to motivate the problem why this problem of missing features is important in bandits. And then I will try to give a very high level overview of multi-arm bandits, because whatever I talk in terms of collaborative bandits is built on top of multi-arm bandits. And then I will give you some flavor of algorithms that can handle this missing information. And finally, I will talk about one interesting application of collaborative bandits to AI for social good. In particular, some of these algorithms we have been using them to improve mobile healthcare programs in collaboration with some NGOs. We also have several applications in terms of Fitbit. So if many of you might know, Fitbit is a smartwatch which helps tracking users' health information. And we have been running some studies to see if we can use Fitbit to improve physical activity of users and improve their health. So if I have time, I will talk about it, and finally I'll present some open problems for you to work. Okay, so I know many of you might have already heard about bandits, but just to refresh your memory, I will try to describe it again. So bandit optimization is a very nice theoretical framework which helps you study decision making under uncertainty. So let me explain this a bit more. So if you take any real world recommender systems like Netflix or YouTube or any other platforms, so usually when a user comes to this platform, it's a black box to the platform. So that is, you don't really know anything about the user, and as a system or as a recommender system, your goal is to really identify the preferences of the users quickly so that you can recommend good content to users. Bandit optimization provides a framework for studying this problem. At a very high level, what you do is you get to interact with the user over multiple iterations. The user provides you some feedback, and then you refine, try to understand the user's preferences as quickly as possible. Bandit optimization as a field has grown exponentially in the last few decades. In fact, if you see any modern systems, they use bandit algorithms in some form. So it's not just YouTube or Netflix. If you see Apple smartwatches or Fitbits, they deploy a lot of bandit algorithms. They always try to understand you by showing some new content and observing your interests. These are also used in educational content. For example, Duolingo is a startup it's a company in US. It's meant for teaching languages to users, and they do employ bandit algorithms a lot to quickly to identify what's the best content to show to the user so that they can quickly learn the language. Okay, so that's enough of bandit optimization, but what's done in the theoretical research in bandit optimization till now is that most of these existing algorithms, they assume the feature or the contextual information about users is available to us. So what I mean by features is it could be anything like demographic information, or it could be your location information, or some such relevant data which will help in predicting your preferences. So most of the algorithms assume this information is given, but what happens in practice is this information is not available to you because of several reasons. So just to give you some examples here. So one important example is healthcare setting. Usually in healthcare, users are not willing to share their private information, like they don't want to share their health records or their history of conditions and so on. And even without this information, you really want to understand these users. So that's one example. And another example is could be in AI for social good settings, where these NGOs which try to work on these AI for social good applications, they don't really have the infrastructure to collect these features. So for example, typically NGOs working in third world countries, they try to cater to millions of users, but they don't have the resources to really collect their demographic information or their location information and so on. And finally, the missing information, missing features could be because of government regulations as well. So recently, European Union passed some regulations saying that you can't really collect all forms of data about users. So you are only restricted to collect some kinds of users which are non-identifiable about the users. So all of these reasons clearly show that it's important to consider missing information in bandit algorithms. And it turns out algorithms that are oblivious to this missing information, they often tend to perform very poorly in practice. Okay, I will explain on this a bit more why they perform very poorly. So before doing that, let me first introduce a very canonical problem which captures this latent or missing information. So I will call this problem the multi-user multi-arm bandit problem. So you have a lot of users, for example, in the case of Netflix or YouTube, these could be in the order of millions or billions. And for every user, there is a multi-arm bandit problem associated with each user. So that is for every user, there are some millions of items, and you need to identify the best item for every user. And what's the missing information here? We assume the users can be grouped into some very few number of clusters or latent groups, which you don't know beforehand. This is the latent information. And users falling within the same group tend to have similar preferences. So you might ask, why is this a valid or relevant problem to study? So what happens is very often in practice, users can be grouped into a small number of clusters. If you take YouTube, perhaps users who like sports can be grouped into one cluster, or users who like music can be grouped into some other cluster. So in fact, in most of the applications we did look into, the users can be grouped into some latent clusters. It's just that you don't know them beforehand. So this is the canonical problem we will be considering this talk mostly, but this I chose this mainly to simplify the our theory results that we have, or so that you can easily understand, but some of these ideas can be extended to more general latent information. And our goal is to quickly learn the user preferences given this model of missing information. Okay, so now let's get back to the question of why existing algorithms don't work well in this setting. So what could one do with existing algorithms? So one naive thing to do is you can treat each user independently and try to run a separate multi-arm bandit problem for each user. So if you are familiar with multi-arm bandits, you could run some popular algorithms like upper confidence bounds or Thompson sampling style algorithms. Does anyone know these algorithms? Have you heard of these? Okay, so I'm assuming you might have been given this in the last 2 days, you might have looked into this. But yeah, so you could treat each user independently and run any of your favorite multi-arm bandit algorithms to learn their preferences. But what's the downside with this? So the main downside with this is it requires lot of exploration. So think of modern recommender systems where you have millions of items. So for every user, if you go and explore independently, you will waste like 1,000 rounds of interactions or hundreds of thousands of rounds of interaction just to learn their preferences. And if you are so slow in identifying their preferences, people will just leave the system, or they will just drop out of healthcare studies or such things, which is not desirable. So the other I think one could do is treat all the users as the same, ignore the latent information totally, and try to fit a single multi-arm bandit model for all the users. This will resolve this exploration issue in the sense, since you are only fitting one model, you can aggregate information across users to quickly learn this common model, but it's again very bad because this will not be really a personalized model, because you will be recommending the same content to all the users, and again this is not a good thing to do. So hopefully I have convinced that, yeah.
So is regret and this quality of recommendation, is there like a trade-off?
I will come to that. Actually, usually we do care about regret. It's related to quality of recommendations, because in an online learning system like YouTube, we don't really care about identifying the best term. All we care about is across the interactions, all the interactions with the users, how good are your recommendations. That's the only notion we care about. So regret is the main metric we will be considering in this talk, and that's the most relevant metric for us. Okay, so the punchline here is that we in this work we try to design these collaborative algorithms which try to collaborate across users with similar preferences. So what I mean by that is we try to do this online clustering. Since I am working with these latent clusters, I am giving the algorithm for that setting. So what we do is we try to learn these clusterings of users on the fly, and then we try to simultaneously collaborate across users falling within the same cluster to learn a preference model for them. So there are two problems here. Let's first look at the clustering problem. So you might have heard about clustering in the traditional offline setting, where you are already given data beforehand and your goal is just to identify clusters in the data. Some popular algorithms are like k-means clustering or these things. But if you see, that itself is a very hard problem to solve, and you will see research papers or theoretical results coming out just on offline clustering even now. They are trying to give computationally efficient algorithms or algorithms which have good statistical guarantees. So the challenge here is that we need to do this clustering on the fly. You need to actively query information about the users, and then you need to do on the fly clustering. So that's challenge number one. And the other challenge is we don't just care about getting the clusters. We really care about identifying the preferences of the users. So we need to converge on those preferences very quickly. So that's where the collaborative angle comes in. In the rest of the talk, we'll see how both of these ideas can be used to come up with algorithms. Okay, so at a high level, what we do is we design these collaborative bandit algorithms, which require only exploration which scales as items plus users. So this is exploration needed across all the users. So per user, the exploration you need is items by users. So you need not even explore. So let's say a number of items and users are the same, which is in the order of millions. Then essentially it's saying is per user you will only explore 2 or 3 rounds. Which is very small compared to a naive algorithm which we saw just now, which usually requires exploring all the items for every user. So so the algorithm that we design have this property that you need not explore too much, and consequently you get very less regret. And one thing I have to say is these algorithms are really being deployed currently in Google, in the sense we are trying it on YouTube and Fitbit and these are things. So some of these ideas do work out, and there are a lot of open questions here. So we will try to discuss them over time. Okay, so I'd like to just stop here and see if there are any questions.
Actually, I have not a doubt, but like suppose we have some person A, and he has some set of preferences, or like set of preferences. Now some other person joins, suppose YouTube, and now he's on the same track where he's kind of like having sort of same preferences, and now we use the what we say like our recommendations to the person B also. So is it like, is that how clustering is working, or like
Yeah, at a
like
high level,
this
we try
way we are
to
saving lot of data and like.
yeah, we try to, whenever a new user comes, we try to identify which of these clusters the user belongs to very quickly, and then we try to use the preferences of users, existing users in that cluster, to quickly converge on.
It's a dynamic setting, so the
Yeah.
cluster changes. With
Clusters
time.
can change over time. Yeah. Yeah, I'll come to the algorithmic details soon. I haven't really touched upon the algorithms. Probably in the next section of the talk, you will see the algorithmic details.
Does YouTube use a bandit model or like a recommended system, like machine learning recommended model?
These are online. These are Bandit and RL models. I mean, it's complex to answer. They have tons of models sitting everywhere, but some of them do use RL and Bandits. Probably, if you look at more recent companies like TikTok, they would be purely relying on RL because their infrastructure is so new, so they can quickly adapt to all these algorithms. Google is a bit old, so they have archaic systems.
Recently, YouTube also has this like see new videos. Like sometimes we get into a rabbit hole,
Yeah.
and then it's unable to access like different content.
Yeah, that's an issue we are trying to address, but I guess there is no easy fix there. But yeah, again, there are some RL algorithms being used, some of them. Yeah. Okay, so now let me try to quickly give you a recap of multi-arm bandits. Since many of you might already know, I'll try to just breeze through the slides. Okay, what is multi-arm bandits? So multi-arm bandits is usually studied in the single agent setting, where at every round you recommend some item to the user and you receive some reward or some feedback from the user. So here AT represents the action that you chose at time step t, and RT is the reward that you get. And we work in this stochastic setting where we assume the reward is drawn from some unknown probability distribution. So there is a probability distribution associated with each item or reward, and you are seeing a sample drawn from this distribution. And what we really care about is the reward that you accumulate over time. We want to ideally maximize it. And regret really captures this in one way, where in regret you also try to have a baseline comparator, which essentially says what's the maximum reward you could have accumulated if I already told you user preferences beforehand. And regret simply measures how far away are you from this optimal policy of which recommends the best possible action every time. So yeah, as I said, a lot of algorithms have been designed for solving this problem. So the main challenge in solving this problem is that since you don't really know anything about these actions, you really need to explore them before committing to something. And how do you explore is the key question. How do you optimally explore? And getting this right exploration exploitation balance is the key challenge. So since many of you already know UCB and Thompson sampling, probably those are the most popular algorithms that are out there for solving these multi-arm bandit problems. But in this work we don't rely on UCB and Thompson sampling. There's a reason for it, but instead we will use something called phased elimination. Has anyone of you heard phased elimination? Okay, let me go into the details of it. So why is phased elimination interesting is it has a clean separation between exploration and exploitation phases. So unlike UCB, which tries to mix exploration and exploitation together, phased elimination has a separation between phases, which helps you theoretically analyze these algorithms, which makes the theoretical analysis much easier. It's not just that, even in implementing these algorithms in practice is much easier than UCB or Thompson sampling. So Thompson sampling is a Bayesian algorithm which requires sampling from the posterior, and sampling usually is not that easy. So people tend to avoid Thompson sampling. UCB has its own issues. It involves solving some non-convex optimization problems, but phased elimination doesn't have a lot of these challenges. Okay, so let me explain what phased elimination is. So let's assume there are some n number of arms. This plot is just showing the true reward of every arm, which is unknown to us. So as the name suggests, phased elimination goes in phases. So in the first phase, all the arms are active, and you just simply try to pull each arm multiple times until you get to you get a rough estimate of rewards of each of the arms. So to be even more precise, you want to get a delta accurate estimate of each of the arms rewards. So by delta accurate I mean, so let's say for arm A, mu A is its true reward, let's say the true expected reward. So you generate some samples, let's call x1 to xn from the distribution of arm A. So you want to, what you want is this average, empirical average, to be within delta of the true mean of the arm. So how would we know when we are delta close to the true mean? So there are classical results in statistics. Is any one of you familiar with Hofding's bounds? Yeah. So Hofding's bound says that if you have n IID samples from a distribution, you are roughly 1 over root n close to the true mean with high probability. So essentially, if you want delta accurate estimates of the arms, you just sample each arm 1 over delta square times. So that's how you know when to stop the sampling process. So what this algorithm does is, initially it says sets a precision level delta is equal to some large number. Let's for simplicity call it half. So you sample each arm until you get a precision of half. This is the exploration phase. You just purely explore, like randomly sample each of the arms. And then there is this exploitation phase where you just try to eliminate arms which look suboptimal. So by suboptimal I mean, let's say mu hat 1 to mu hat m are the estimates of empirical mean or estimates of the means of each of the m arms. Then you try to see, so you have a confidence band for each of the arm. So let's say this is mu hat 1. We know that its true mean can lie in any of this 2 delta interval of mu hat 1. And let's say there is some other arm whose confidence band doesn't intersect with the confidence band of this. You can be more or less certain that its true reward is less than the best arm. So you simply eliminate it. So basically you just look at the empirical best arm, try to see whose rewards are 2 delta smaller than it, you just eliminate those arms. And you repeat this process. So now you have fewer number of arms. You try to estimate their means to even more precision. Instead of half, now you go double the precision, like 1/4. And then you try to sample each of the remaining arms independently, and then again do this elimination phase at the end of the exploration. So finally, you repeat this process multiple times, and you will hopefully be left with a single arm, and you just keep on pulling that. So is the algorithm clear? It has this exploration and exploitation phases separate. So it turns out you can easily show regret bounds for this algorithm. It's actually very 2 simple steps. So you can show its regret is bounded by square root number of items times t. T is the time horizon. And this turns out to be minimax optimal for multi-arm bandits. So the proof actually just relies on 2 steps. One, since you already know the Hofding's bound, you know that after n generating n independent samples, the empirical mean is 1 over root n close to the true mean. Okay, the second step is this. So let's call delta I to be your suboptimality gap. That is how suboptimal arm I is compared to the best arm. So for now I am assuming item 1 is the best arm here. So you just try to see how suboptimal an arm is compared to the best arm. Some very simple argument shows that you just need to pull an arm 1 over delta S square times to figure out whether that's suboptimal or not. So every arm I you can show will be pulled only 1 over delta S square times before it's being eliminated. It's a very simple argument follows from Hofding's bound, because if you already pulled something 1 over delta S square times, you can estimate its mean to within delta I precision, and that's enough information for you to eliminate that arm. So that's it. The proof is just simple, these 2 arguments. Since you know how many times you are going to pull each arm, you can simply compute the regret. The regret is nothing but the number of times you pull that arm times the suboptimality gap. So a simple calculation shows that the regret scales as square root items times t. Okay, any questions with phase determination?
I have a question.
Yeah.
Multi-arm bandits talk about lack of the probabilities or the preferences.
Yeah.
But you talked about lack of features. So what are those lack of features?
So features are nothing but every user has some feature information, right? So multi-arm bandits is featureless, like you don't need information at all. But when you have millions of users, it's hard to fit multi-arm bandit models to each of the users. You really need to fit some non-linear, more complex function. So essentially, the features help you. So let's say there is a user u whose feature vector is xu. So traditionally, when you deploy a bandit system, you try to learn a model which can give you your preference. So f of xu predicts the preference of the user. So xu is a feature vector, f is some model. So multi-arm bandits doesn't do this. Multi-arm bandits only works for one user. So you don't need the function at all. You just need to find the one item for that user. So in real world, since you have millions of users, you need to come up with some nonlinear predictor which takes this feature information and outputs the best vector or best item for each user. And in practice, this information could be missing, some of this information. And we really want to learn preferences for millions of users even without this feature information.
Do we have any bounds on the precision we take?
Sorry, could you repeat that?
Do we have any bounds on like how do we understand what precision we take?
So you just decay it exponentially. You can start with any reasonable constant like 1 or something.
Any bounds like as if precision divided is. So do we
Uh,
have any bounds on it?
So ultimately, there is a trade-off. If you want a very high precision right from the beginning, you will pay a price because you will be exploring suboptimal arms a lot. So the key is you need to slowly decay. There should be a decay in this precision, or you exponentially decay it. So if you, as I was saying, if you have a delta precision, if you need delta precision, you need to pull all the remaining arms 1 over delta square times. And if you really make the delta very small right from the beginning, you will pay a lot in terms of precision. And anyways, the game lasts only t rounds, so you will, the maximum delta that you choose is roughly like, the least possible delta that you will go to is roughly 1 over root t or something like that, because you have an exponential decay. Okay, any other questions? Okay, so let me continue. So now let's come to the multi-arm bandits and collaborative bandits again. So here the problem is slightly different. As I said, we have multiple users, and our goal is to really identify the preferences of each of the users even without knowing any of their contextual information. So what happens is every round a random user u of t is picked and the user comes to the system and you make a recommendation AT and you observe a noisy reward RT for that user. We do not make any assumptions about this UT, we just assume it's some random process, the users are randomly picked. And our goal is really to minimize this per user regret. So this is essentially just summing all the rewards that you accumulate for all the users over time, and you just compare it with the best possible item for every user. So this mu UT star is nothing but the best reward you would have gotten for a user UT. So and you want to compete with that best possible reward. So just to formalize the latent cluster assumption that I made previously. So just look at the users cross items reward matrix. This is a huge matrix, usually like million cross million matrix. And each entry in this matrix is just saying the reward, what reward you would have gotten for this user if you showed this item. And we are really assuming there are groups of users such that they have very similar preferences. So essentially the rows in this matrix can be clustered. Yeah.
So this valuation that you are giving, so that is based on say the amount of video watched or like
You mean the rating rewards?
Yes.
It could be anything. So typically depends on the setting and the way you formulate.
Like most people won't be given like this.
Yeah. So this is just for some toy illustration, but in practice this reward is some very complex function. Usually depends on watch time, whether the user quit the YouTube player or not, something like that. So I mean there are a lot of other metrics which are crucial than just like dislike. It's a complex function. It's made up of some hundreds of parameters. Okay. So as I was saying, this assumption of latent cluster C is very practical. So just to give one illustration here, this is a movie lens data set which is publicly available. This data set contains the preferences of users for every item. So users give some ratings for some movies, and if you take this data set and cluster them per user based on users, you will see nice clusters forming. So this shows that usually in practice this cluster assumption is reasonable to make. So yeah, so as I was saying, this problem is relatively new. This was only people started looking into this missing feature problems only in the past decade or so, and our real contribution is to so most of the existing works make some unreasonable assumptions, like they assume the clustering is known, or they don't get the optimal regret guarantees. So the main contribution of this whatever I am presenting right now is to really give some algorithms which get optimal regrets without assuming the clusterings are known to the user. So here is the main result. So before jumping into the algorithm, let me present the main result so that you don't get lost. So let's say you don't collaborate, so instead you just fit a simple multi-arm bandit instance for each user, then the per user regret scales like this. It's just square root items times user t. Whereas the per user regret of a collaborative algorithm scales like this, 1 plus items over users times t. So you can see there is an order of magnitude gap between these two rates, and if you see the plots on the right hand side, these are some synthetic experiments that we ran on Netflix dataset and movie lens datasets. So UCB is your standard basic algorithm where you don't collaborate across users. So if you see, the regret of UCB is much larger than this. Is the green line is our algorithm. So it's 1 order of magnitude better than UCB. These are just synthetic, or I would say synthetic dataset experiments. Towards the end I will also show you some real numbers on real problems. Sorry, how much time do I have? Okay, so just a few points about this result. So the rates are minimax optimal. By minimax optimal I mean this is the best you can achieve even from an information theoretic perspective. So these are worst case bounds, but the dependence on number of clusters, which I haven't really shown here, is slightly suboptimal in our rates, but there are some follow-up works which improved upon these rates recently. So the results can be extended to slightly more general setting where the users, for users falling within the same cluster, their preferences need not be exactly the same. They could be epsilon away from each other. Even then the same algorithm works out. Okay, so now I will jump into the algorithm, but before describing it I would like to just stop here and see if there are any questions.
What was alternating minimization?
In the synthetic experiment.
Sorry, I forgot to explain that. So that's a heuristic which has been proposed in the literature a few years back. So it doesn't have any theoretical guarantees, but what they do is how to explain this. So if you take the reward matrix, let me go ahead one slide. So if this is your reward matrix, right? this has a low rank structure to it. Is everyone familiar with low rank? What a low rank matrix is? It essentially says that, let's say you have some n cross m matrix R. You can write it as a product of two matrices, one tall and one thin matrix. And R is usually much smaller than n comma m. That's a low rank matrix. So essentially, the clustering assumption we placed says that this matrix is a low rank matrix. So what that alternating minimization does is it tries to run a UCB algorithm to estimate this and then another UCB algorithm to estimate this. It's like if you are familiar with EM style algorithms, it does expectation maximization style algorithms, but it doesn't come with any theory, and it's also, I believe it's not optimal. That's also showing up in the rates. It is slightly sub.
UCP is so much worse than the others.
Yeah, that's because UCB doesn't collaborate across users. It treats each user independently. Yeah, it's basically oblivious to this latent information. Yeah.
Okay, so it's basically ignore the clustering information that you are aggregating.
Yeah, which we are trying to estimate. UCB doesn't estimate that.
So just one thing. So do you think that if the clustering quality was very high, that would show up in their final performance of
Yes.
the recommended system?
So you're saying the other way to put it is, if the clustering quality is bad, would it hurt the performance?
Rather,
Yeah. If the clustering is bad, it would hurt. So really, the goal is to identify these clusters accurately. Otherwise, we will be recommending wrong content to users. I mean, if the clusters are such that they are inseparable, then it's fine. But we don't want to make really bad mistakes of placing one user who is at a distant cluster into some other cluster.
So what is the cluster metric do you look for? Coherence is what you're looking for, right?
Cluster metrics. So currently, we don't necessarily look at clusters because all we care about is regret. Even if you don't identify nearby clusters. So let's say there are some overlapping clusters. Even if we don't separate them, we are fine with it.
So these are people who have interest in both kinds.
Both kinds, or they're just very, it's very hard to say. And all we care about is separating distant clusters like these two. And this we can show theoretically we will separate. It's just that we may not be able to identify this, but we don't care about this. We care about regret. But to give more precise statement, I think we can say something like this. If the distance between clusters is greater than 1 over root t, I think we can separate them. T is the number of rounds of interaction with the users. So basically, if the distance is much smaller than 1 over root t, you don't even have the opportunity to separate these because you don't have enough samples to separate them. So,
If these rounds are somehow they are very similar to each other, but you have a lot of rounds, but they all are very similar. That would also create a problem of separating them.
rounds. By similar, you mean are we recommending the same content or?
Like the information that is coming through across the round, they're all very similar.
So depends on our algorithm. So our algorithm really needs to collect more information by exploring. If our algorithm stops exploring, then we can't do much. So that's where the algorithm design matters. We shouldn't stop exploring. We need to intelligently explore so that we don't converge to some suboptimal solutions. So I guess that's where the design of UCB also comes in. Like UCB style algorithms, they don't recommend the same content. They try to recommend new items whenever they are unsure of some item, so that you don't converge to suboptimal solutions. Okay, so let me jump into the algorithmic details. So before presenting the algorithm, let me just give you what are the key ideas that we have here. Okay, the first key observation is this matrix is low rank matrix. Okay, so what we do with this? So there is a lot of work in offline low rank matrix completion. What I mean by offline is, let's say all the data is given beforehand to you. Matrix completion, what it tries to do is, let's again take this n cross m matrix, which is huge. Is this visible or should I? Okay, let me just write it this. So let's take this huge matrix n cross m, and let's say its rank is R. That is, you can just do this UV decomposition. with rank R. So, matrix completion, the traditional offline matrix completion, what it does is you can randomly sample a few entries from this matrix, and you can finish this matrix by just observing n plus m times R observations. So, let us say R is just a small constant like 5 or 10, then it says that even if you need not observe the entire n cross m entries in this matrix, you just need to observe n plus m times 10 entries and you can finish this entire matrix. That is because you can decompose this matrix into UV, and the number of degrees of freedom you have is simply just n times R, m times R. So, the degrees of freedom you have is very less. So, offline low rank matrix completion is really well studied. There are really good algorithms known for it. In some sense, what we are trying to do in this multi-user multi-arm bandit problem is do online low rank matrix completion. So, that is we want to really estimate this matrix as quickly as possible without pulling all possible arms for every user. So, this is one key insight. We are going to rely on these offline low rank matrix completion oracles in our algorithm. Again, the reason for relying on these offline matrix completion oracles is these are really well studied and they are really super fast algorithms which can scale to matrices of size billions. So, it is very important to make use of them. Okay, the second key idea we use in our algorithm is phased elimination. Okay, here is the reason why we do not go with UCB and Thompson sampling, which are probably much more popular than phased elimination. So, UCB and Thompson sampling, the arms they pull, they are dependent on the history. So, depending on history you decide which arm to pull next. This creates problem for matrix completion, because matrix completion assumes the entries are IID, in the sense they are independent. Without that independent assumption, it is very hard to do matrix completion. So, just to give you very intuitive reason for this, why that is the case, let us say all the entries you observe are only for row 1, then there is no way you could complete the matrix. So, it is very important to get IID samples for matrix completion. So, and UCB and Thompson sampling do not guarantee that. So, that is why we go with this phased elimination style algorithms which randomly pull arms for users instead of history dependent policies. Yeah. Okay. The third algorithmic idea is doing clustering on the fly. So, once we somehow get an estimate of this low rank matrix, then we try to cluster rows which look similar to each other, and then try to collaborate across users within the same cluster, so that you can get a even better estimate of their preferences. Okay, so I hope that algorithmic ideas are clear. Let me now jump into the actual algorithm, what it does. It follows the same phased elimination framework that I described just now. So, initially you place all the users in the same cluster and you keep all the items for all the users as active arms, you do not kill anything. And then you try to randomly sample some items from this user cross item matrix. Your goal is to estimate this matrix to some precision, half or something, some delta precision. So, this is where the low rank structure comes in. So, we need not observe all the entries in this. Instead, even if you just randomly pull only n plus n times R elements in this matrix, that is enough to estimate this entire matrix to some precision delta. So, the key observation is UCB does not rely on this information. UCB just tries to randomly pull items for all the users, it does not rely on this information. So, once we get this matrix, we do matrix completion, and then we try to do eliminate arms which look suboptimal for each of the users. This is the same standard step which I described just now, where you see if there is an arm which is 2 delta away from the best arm, you just simply kill it. And then the final step is you cluster users. So, you look at the remaining arms, active arms, and you cluster users depending on whose rewards look similar to each other. Here you could use k means or something, because these are just IID samples that are generated by phased elimination. And then you continue this process in the next phase you try to exponentially improve your precision. Instead of half precision, you try to go to precision of 1 or 2 power I. And then over time you can actually guarantee two things. One is you can identify the clusters as long as they are slightly far away from each other, and you can also show that the best items never get eliminated in the algorithm. Okay, so before going into the proof, I just want to stop here and see if there are any questions about the algorithms.
How many rounds do we usually have?
It's logarithmic in T usually, because your phase length rounds in the sense T, or is it phase elimination rounds?
Like phase elimination.
The number of phases is logarithmic in T.
Yeah, because
It's the precision is exponentially decaying, so you need exponentially more samples every round to do it. Okay, so the proof actually at a very high level, I mean there are a lot of nitty-gritty details here, but I am not going into it. At a very high level, it follows again the same phase elimination style ideas, but the key observation is to get to delta I precision, you just need these many samples because you are doing low rank matrix completion. You don't need these items cross users many samples. This is the key observation, and you can use the same phase elimination analysis to show that the regret you get is square root items plus users times T. So there are a lot of details in the sense matrix completion only works under some assumptions. Trying to make sure that your algorithm satisfies those assumptions is one more challenging part, but I am not going to go into those details here. But I would like to say that since we published this work, there are a lot of other works which came out and tried to simplify or improve some of the rates that we have here and try to simplify the algorithms even further. If anyone is interested in those things, I can point you to some of those works. Okay, so finally, I will talk about one particular application of this work to mobile healthcare programs. So I know Aparna might have talked about this, I am not sure, but I will try to go into a bit more algorithmic details here. So the main problem that we are tackling here is how to reduce maternal mortality. So especially in India and South Asian countries, maternal mortality is very high, and one of the targets of United Nations is to bring down this mortality rate. And in this work, what we are doing is we are working with this NGO called Arun, which runs this program called Kilkari. So what this Kilkari program does is it recruits pregnant women all over the country. I think currently they have 3 million subscribers, and then they try to send automated voice messages to them every day throughout their pregnancy. The information that they share could be around child health or pregnancy or immunization or any of these. The important thing is this program caters to people with low socioeconomic status, and this particular thing creates some challenges for us. So in particular, the key challenge is the listenership is very low for this program. The main reasons for this are, there are multiple reasons. One is this, some of these people, they don't even have access to phones throughout the day. They can only probably have access to phones when their husbands are home or some other reasons. So in such cases, if let's say they have access to the phones in the evening, and if you end up calling them in the morning, there is no way they can get the information. The other challenge could be some of these women might be going out for work, or they might be busy with household responsibilities. So there could be a lot of these unknown confounders which we don't know, mainly because this program is run at a really big scale and the NGO doesn't have the resources to collect this information. So these are unknown confounders for us. And why is this challenging? Because without this information, it's hard to know when to call a beneficiary. And if you don't really reach to these beneficiaries on time, they tend to drop out from the study. Let's say they don't receive a call for 1 week, they just simply try to ignore this information over time. And this also puts burden on the NGO's resources, because these are automated calls which are made, and the system can only handle a few calls. If the users are not picking their calls, the system tries to retry, make multiple attempts, and the more attempts you make, the more burden you are placing on the infrastructure. So there are all of these concerns. So here is some actual numbers from this that we got from this NGO. So there are only 35 to 40% of people who pick their calls in the first attempt they make, and even after 9 attempts, there are only 75% people who pick up the calls. So the key question is, when do we call a beneficiary? And now I'll show you how the collaborative bandits can be used to solve this problem. But first I want to know if Aparna covered these things yesterday, or is this okay?
Not these exact.
She just explained that this is the service they are trying to.
I see. Okay.
Not the specific.
Okay. Maybe I'll go into the algorithmic details more. Okay, so how do we pose this as a multi-user, multi-arm bandit problem? So each user is a beneficiary, and the arms for us as the time slots. When do you call the beneficiary? And this problem nicely fits into the framework that I just described, because you really don't have any information about these beneficiaries, about their availabilities or phone availability or working hours or anything. So this is really, all of this information is latent to us. And it's important that this study runs for very short duration. It only runs for 9 months or so, and it's really important to identify these right time slots to call users very quickly. If you are slow to identify this, they just drop out of the program. Yeah.
Pre-recorded messages and everything, so these are sent over messages or?
No, these are voice calls.
Robocall.
Yeah, robocalls.
Can I ask a question? Why can't we just solicit this information from these versions? What is it?
Yeah, so the NGO doesn't have, as I was saying, this is like really large scale program where there is probably one person on the ground who is assigned to recruit these women. They don't have that resources to collect that information. I mean, even if they collect some information like locality, that may not be really useful for us, because locality doesn't dictate whether a woman will pick up a call someplace or at some particular time or not.
Yeah, not look at the timing of like this husband, they're sharing the phone.
Yeah, they don't collect such information. I think it's just the scale of the program, and two, maybe.
Also the information storage.
Yes. And there is one more challenge. The thing is, these NGOs, they don't want to reveal the private information of the users. So for us, since they are collaborating with Google, Government of India has some restrictions saying you can't share identifiable information at all. So all they can share is locality information with us. So that also puts some additional constraints for us to solve this problem. Okay, so again, our goal is to optimize regret, but there is some other metric I will talk about, which is number of retries you make before a successful call. But we are not directly optimizing for it, but both of these are somehow correlated to each other. You optimize regret, you will reduce the number of retries that you need to make before a successful call. Okay, so the core philosophy is still the same, but one key observation that I want to point out is, we took this real pickup rate matrix from this study from the NGO. We looked at this users cross time slot matrix, and we did notice that it has a low rank structure. Okay, that is, there are probably 2 or 3 eigenvalues or eigendirections which dominate everything, and the rest are just noise. So okay, there is one key challenge. This is low rank. This is not exactly clustering assumption that I made, that I described in the previous part of the talk. So low rank structure turns out to be much more general than cluster structure. So we need slightly different algorithms to solve this problem. In fact, we have been spending time, we almost spent 6 months on this problem trying to get regret optimal algorithms for low rank structure. But as of now, we don't have any success. This is still an open problem in the community. There are a lot of papers coming out trying to solve this, but it's just that they are nowhere close to getting the optimal regret rates. Okay, so yeah, so as I was saying, instead of cluster structure, instead of rows being exactly the same, we don't have that anymore. We have this low rank structure. Yeah.
What is this low rank structure in this particular setting mean? This time versus what is this metric?
So this is the
time
pickup rate matrix. So what's the probability of a user picking up a call at this time slot?
Yeah, what does low rank here represent?
So low rank implicitly means there are
Small time interval is there.
probably not necessarily. I think it just means, okay, the one way to view low rank is, think of these as user embeddings. These are two-dimensional user embeddings associated for each user, and these are the time slot item embeddings. So essentially what this is saying is the users can be embedded in some very low dimensional space.
So doesn't that mean that there's a lot of correlation?
There is some correlation between them. Yeah. It's not exactly cluster structure, but it's just saying that there are these latent features, like these two-dimensional latent features here in this example, which we are unaware of, and these help you predict the preferences very easily. And our algorithm essentially tries to estimate these latent features for arms and users simultaneously.
Bit vaguely, low rank implies that there will be less number of clusters, right? Because then it will help us to.
Low rank in some sense implies clusters, but low rank I would say is much more general.
Yeah, but vaguely, like it's general,
yeah.
but vaguely it will suggest that we can have less number of clusters.
Yeah. Yeah. So the other way to view it is think of low rank as saying that you can embed these users in some very low dimensional space.
Yeah.
So that's the other way to look at it.
Yeah, dimension reduction. It's some of that, right? From this
Yeah.
entirety, you want to be able to reduce the dimension.
The key challenge is doing this in an active way. Like this is an online learning setup. So as I was saying, this problem is still open. I do see 4 or 5 papers coming out every conference, but they tried.
Online problem.
Yeah, the online low rank matrix completion. It's very challenging. Even the algorithm I'm going to present, it's only a heuristic. We don't yet have an analysis for it. So if anyone is interested, very much happy to work on this problem. Okay. So as I was saying, we don't have an optimal algorithm, but we try to design some very simple heuristics that are easy to apply in practice. The very first heuristic we come up with is greedy matrix completion. So think of this as phase termination, but with only one phase. You just first have an exploration phase. You just randomly pull arms for users or call them at various time slots randomly. You collect some information about these preferences. You do some robust matrix completion. I will tell you what this robust matrix completion is later on, but for now just think of it as matrix completion. So basically you try to complete this entire user cross item reward matrix in this exploration phase, and in the exploitation phase you just simply try to use the data that you estimate, the model that you fit to recommend call users at their appropriate time slots. So this is just phase termination with phase length 1. Okay, the reason why we study is 2 things. Phase termination can be optimal if you somehow know how much exploration phase, what's the length of the exploration phase to choose. So in the sense, so if you set the exploration phase too small, you won't have enough information to recommend items to users. If you set it too long, you will be wasting your resources just randomly calling users, which is both are not good. But if you set it properly, you can show this algorithm is optimal. But in practice, no one knows how to set it properly. In fact, you can show theoretically that it's impossible to find this optimal exploration length beforehand or even during the course of the algorithm. So theoretically, this might look like an optimal algorithm, but it's not, because it assumes that this optimal exploration length can be set, but it can't be set in practice. Okay. So what we do is we also proposed phased matrix completion style algorithm, which is like phased elimination and goes in multiple phases. But here, unlike low rank structure, we can't do hard eliminate the arms. Instead, we need to keep them alive even if we believe they are suboptimal. There are a lot of theoretical reasons for it. But at a high level, what we do is we first again explore, but this exploration length is some small number like 1 or 2 days, and then you complete this matrix to whatever precision you want. I mean, to whatever precision you can get from this data, and then you do some special exploration called Boltzmann exploration. So this is where the algorithm that I present for the cluster assumption differs from this low rank assumption. Instead of eliminating the arms entirely, we keep them, but we do a soft elimination of sorts, like whatever arm we believe is not optimal, we try to reduce the chance of it being pulled. That's all. And Boltzmann exploration is a way to do it. This is a popular exploration that is used in reinforcement learning. And the algorithm continues in phases again, like at the end of each phase you try to do the matrix completion, which is like exploitation, and after that you do exploration using Boltzmann exploration. Okay, so what is robust matrix completion that that is used here? So what happens in practice is the data is very noisy. These have long tails, and very often whatever sub-Gaussianity assumption or Gaussian distribution assumptions that we make, they break in practice. So you really need estimators which can tolerate high level of noise in your data, and traditionally matrix completion doesn't do that. So we do some variance reduction techniques. One particular variance reduction technique which some of you might be familiar is called bagging. If you are familiar with random forests or these things which do bagging, it's a variance reduction technique. Essentially you fit multiple trees randomly and then you just try to aggregate the results, and that's what we do here in some sense. We try to subsample the data, try to do matrix completion each of the subsamples, and then we do something called median of means estimates, which help you get a better estimate of the mean. Okay, basically the high level idea is you need to do variance reduction in practice. If you don't do that, these estimators turn out to be very bad. So the next is Boltzmann exploration, as I was saying. Instead of doing a hard elimination of arms, we try to do soft elimination. If the reward of an arm is small, then the probability of that arm getting pulled is small. Essentially, it goes down exponentially. Yeah, unfortunately, we don't have any theory for it, but it works well in practice. There are some practical considerations that needs to be made. Since we are working with the real NGO here, they have a lot more constraints which need to be baked into this algorithm. One particular constraint is they can only call a user, they can only make 9 attempts for a user in a week. How do you encode these constraints into the Bandit algorithm is another challenging aspect. Again, we use some heuristics to get there, which are probably not that important. But let me jump into the experimental results. So what we do is this: we get anonymized call log data from this NGO. By anonymized, I mean we don't have any features available for the users. We have around 2 lakh beneficiaries, and the number of time slots is actually 7. They have 7 different time slots in which they can call a user in every day. And the data they have is this: every call they make, they log whether how long did the user engage with the call, if at all they picked. If they didn't pick, they just leave it blank. And what we do is we use this data to simulate our algorithms. So this is not a live experiment. The live experiments are still ongoing, and we don't yet have results for it, but we worked with the real data and tried to simulate the various algorithms. Okay, so here is how the regret looks like for various algorithms. So this is UCB. It has a relatively high regret. This red is the phased matrix completion, which relies on phased elimination, which almost gets like 20% reduction in regret. Ignore the greedy for now. I mean, greedy is where I said phased elimination with phase length 1. it also has better regret, but it's somewhere in between these two algorithms. Okay, so regret is not the only thing the NGO cares about. They do care about a number of retries. So what I mean by that is number of retries you make, you have to make before a successful call. What this plot shows is this: you divide users into various buckets depending on the level of engagement. So this bucket is very low engagement bucket users, where the chance of they picking the call is very little, 0 to 0.1. Here is a most extreme engagement bucket, where the chance of they picking up a call is almost close to 1. And for each of these buckets, we plot number of retries that each algorithm makes. So the blue is the random baseline which the NGO implements currently. So their policy is very naive. They just randomly call users every day. They don't have any reasonable policy. This is UCB. Orange is the UCB, and green is the collaborative bandit algorithm, the phased elimination algorithms. So you can see phased elimination algorithms can reduce the number of retries by almost 25% compared to UCB. This is very important metric, because now if you reduce the burden on the systems, they can recruit more beneficiaries into the study. Okay, so I am almost at the end of my talk. So let me just try to conclude the key takeaways from this talk. One, the key problem that we are handling is missing information in bandits. So this missing information could be due to various reasons which I explained in the beginning, and it's very important to design bandit algorithms that are aware of this missing information. And this work is really about, in this work we study this canonical or very fundamental problem of multi-user multi-arm bandits with latent information. And we work with two particular forms of latent structure. One is cluster structure and the low rank structures. And for the cluster structure, we give minimax optimal regret guarantees, and we design a phased elimination style algorithms for it. And actually there are a lot of applications we have for this algorithms, which, as I mentioned, we are applying it in Fitbit and YouTube. But the one I talked about just now is just kill curry. So in kill curry, we do see that this improves UCB by almost 25%. Okay, some open problems. One, how do you design regret optimal algorithms for low rank structure? The second most important is, how can you design algorithms for more general latent structures? So in the sense, there could be a lot of other structures just beyond low rank. So classically, there is, if people are familiar with expectation maximization, that's an algorithm that is often used to estimate latent variable models. And EM works very well for general low rank structures. Can you design an online or bandit version of EM algorithm is a question. And the next open question is, how do you extend these collaborative algorithms to contextual bandits? So in the sense, you are given some contextual information but not all. So if you have some partial contextual information about a user or partial feature vector about a user, how do you generalize these algorithms? And finally, how do you extend these ideas to RL, where each user, instead of being associated with a multi-arm bandit, each user has an associated MDP, Markov decision process. Now how do you estimate these MDPs for all the users in a collaborative way? Okay, so that's all I have, and I'm happy to take questions. Yeah.
You just said in this program, you just said there is more work to be done for more latent structures.
Yeah.
So you just said this model you take into account. It is pretty restricted with respect to, say, that information. You said the location-wise information is everything. So what can be more restricted?
So it's not about being that. It's more about the latent assumption that we made. We assumed the users can be grouped into some clusters. That's a latent assumption. But that needs to be generalized. In practice, maybe that's not true. Maybe there is some other latent structure that you can impose. By structure, I mean, so for example, instead of cluster assumption, there is this low rank assumption. Maybe the other form of latents that you could assume is, okay, I'm just creating some instances here. Let's say for every user, there is some variable that you don't observe. Depending on that variable, the preferences of the users could be generated either by a linear bandit model or a neural network model, some very complex models. If you are familiar with Gaussian mixture models, that's one case where there is some latent variable where you decide first toss a coin to figure out which Gaussian to pick from, and that Gaussian is essentially, you can think of it as a reward. So you can place Gaussian mixture model style assumptions on the latent rewards. So, yeah.
Can you expand a bit on contextual bandits?
Yeah, so contextual bandits, as I was saying, multi-arm bandits is for single user. But if you really want to extend multi-arm bandits to millions of users, the way it's typically done is, you assume there is a context vector given or feature vector given for each user. This feature could be user's age, demographic data, location or something. And you want to use this feature vector to learn a policy which maps this feature vector to the user preference. You want to learn a function which maps the feature to the preference. So in multi-arm bandits, there is no need for this feature vector because there's one user, you just need to pick one item which is the best. But when you move to millions of users, you need contextual bandits. And in practice, contextual bandits are what are really used in practice. And what happens in contextual bandits is some piece of information might be available, some may not be available. So how do you handle such settings?
I have a question. So I asked this to Aparna also, like she was telling about how they have deployed the model and the basic structure of the model. So I asked that if we can, like, so with time the data changes, like the stuff changes, and so we have to keep track of it. So can we use this reinforcement learning? So in theory we know, but in practical, what is more efficient, to like the online learning system or just training again and again, time to time?
So
like both are resource heavy things.
Online learning, if you are using adversarial online learning algorithms, they tend to adapt to the distribution shifts. But if you are using stochastic algorithms, like the one we discussed today is stochastic, in the sense whenever you pull an arm, you assume there is the rewards are sampled from a distribution. But there are algorithms which work even for adversarial settings. Those algorithms tend to adapt to changes in distributions over time. But the key challenge is adversarial bandit algorithms are only known in very specific cases. They are not they are super hard to construct, design. In the absence of adversarial bandit algorithms, the other way to do it is retrain these model. In the sense, discard some data from the very long back. So let's say in healthcare applications like Fitbit, depending on the season, people change their walking habits or exercise habits. Like if it's rainy season, they won't walk more. So in such cases, maybe you only want to train on rainy season data, not the past data. Yeah. So usually in practice, such heuristics are applied where you decrease the weights of your data over time. In fact, there is some work in our lab going on which tries to do some meta level optimization to decide how much weight to put on each sample. You essentially learn another weighing function, which could be another neural network or something, which learns how much weight to put on each sample. Those kinds of techniques also can be used to learn the weighing of samples.
I mentioned like the Kilkari is one where you are doing nationwide, but there is some Mumbai localized operation also. So in that, in that also you still use non-contextual bandits as such.
Sorry, I am not aware of that. But do you remember which study that is?
Because she said that it is similar study, but so in that she said that you have more context about the users as such.
I see. I am not aware of that study. Sorry, maybe I can find out.
And also, like small clarification. So the calls that we are making, that is not follow-up calls, but are those the electronic calls that you are talking about?
These are the sorry, what's the follow-up call?
Like the calls that you are making,
Yeah.
the 9 times or
Yeah.
so. What are those calls for?
Oh, they are just follow-ups. Follow-ups in the sense, let's say user doesn't
Like
pick
it's
up
just
the call.
asking them that did they listen to
No,
the
no, no, no.
electronic
It's,
calls? Or?
no, it's not that. Let's say a person doesn't pick up a call at some particular time, they will retry after half an hour, and they'll do that 9 retries.
So, but what is that call for?
Oh, it's for delivering this healthcare information.
So that electronic automated call,
Yeah,
that
automated
is
calls.
that call. Right?
Yeah,
Well, just for delivering the information or like processing it and like there is a person or is
yeah. No, currently the NGO doesn't support that. It's just delivering the information.
How do they change the clusters over time, like in an online manner? Do you guys use k-means or like how is it done?
Yeah, we use scales. So as I said, so yeah, this is where what I mean by k-means. You first try to estimate this matrix from few entries, very few entries, and then you discard arms. After discarding, you try to do the clustering on the remaining users' data. So if two users have very similar rows, in this case red color, think of it as similar rows, you just use k-means to identify these clusters.
Does this work in an online fashion?
Yeah, this is an online.
Maybe to address this, is there a notion of regret in the contextual bandit?
Yes, there is a notion of regret. It's a generalization of the multi-arm bandit regret. So usually in contextual bandits, what you assume is at every time step t, there is a user u who is sampled from some unknown distribution who comes to the system, and there is a feature vector xu associated with the user. And what you assume is the reward you get for pulling an arm A for user u, you assume there is this function which models this reward, and the regret for regret is really defined as and let's say okay, max over u, this is sampled over u minus f star of x u t comma a t. So this is just the expected regret, where the expectation is over the users who are coming as a random process, and this is the best possible you could have done under this model.
TT refers to the ampulla T.
Yeah, what you recommended at time step. And I would say that contextual bandit algorithms are only studied under the stochastic settings, and getting the adversarial algorithms is still an open problem. These are much more challenging problems.
Yeah, I mean that makes sense. I mean, the point is adversarial model would allow an algorithm to be robust against a pathological adversary, but that does not happen in real life. Populations have a lot of patterns that one can mine.
Yeah, that's true, and that's why very often the algorithms that are deployed in practice are just stochastic algorithms. Adversarial algorithms are not deployed.
I would think this should be enough, but the point is how do we learn the distribution in the population, right? That's stochastic knowledge. Given that there is so much restriction on data about people, do you think that gets in the way of having a good hypothesis to start with? That what kind of stochastic distribution adversary we are dealing with here?
So even if you assume you are given access to all the features, learning this distribution on the fly is a hard thing, because we are getting new users over time, and I would say generative modeling, learning the distribution is probably as hard as doing regret minimization, probably. Yeah, probably it will only be much harder than this.
And that's also a more general interest question. I mean, it's independently important.
So yeah, people study, instead of regret, there is another notion people study which is called best term identification. Your goal is to just identify the best term, not the regret minimization. So there people come up with techniques which also try to estimate the distribution of the arm rewards, because there you don't care about regret, all you care about is just a.
They are not the same sort of question. What is the difference? Like, if I could always choose the right arm, that would minimize regret.
Yeah, but regret measures the cumulative rewards over time.
Yes.
Best arm doesn't really care about what you picked in the first T minus 1 rounds. All you care about is that the Tth round output the best thing.
So that's more like this profit, that sort of a situation. Like, I don't know, like I'm at this step whether I'm picking the best thing or not.
Yeah.
It's how do I say? So, but if I had this notion where I was looking for having picked the best arm over a time interval, wouldn't that correlate to regret minimization?
So by best arm, maybe I should be clear. We should best arm in the sense at the end of T rounds of interaction with the user, you output the single best arm, what you think is the best arm.
Not
Let's say for first T rounds, just according to
Yeah.
the situation, I just pick up the best arm from the T rounds I've already played. That might not be the best arm for what I'm going to play. So in that way, I might not be able to minimize regret in what is about to come.
So are you still talking on multi-arm bandits or condition? So multi-arm bandits, if it's stochastic, it turns out roughly they might work out, because all the estimates that you have from T rounds are more or less close to giving you the answer for the best arm. But to be precise, how should I put it? So if you just try to optimize for regret, it won't give you the optimal rates for best arm, because best arm you can do full exploration in the first T minus 1 rounds. So that's why best arm identification is called pure exploration thing. And best arm identification is useful in some settings. Let me give you one case where healthcare. Let's say you are doing vaccine trials and you have 10 variants of vaccines, that is you have 10 arms. And your goal is not to optimize regret, or your goal is to ultimately at the end identify what's the best vaccine you want. So I think that's where best arm gets.